A highly effective way to visualize Dijkstra's algorithm is by examining NPC pathfinding in video games. To demonstrate this concept, we've chosen to show it within the game of Minecraft. It is important to clarify, however, that Minecraft's pathfinding system does not strictly use the original Dijkstra's algorithm, but rather a more sophisticated extension known as the A-star search algorithm. Dijkstra's algorithm finds the shortest path between nodes in a graph by calculating the cumulative cost from the starting point to a given node. Its core cost function is f of n equals g of n. The A-star search algorithm, however, builds upon Dijkstra's algorithm by introducing a heuristic function which allows it to estimate the total cost from the current node to the goal node. This estimate guides the search, making it significantly more efficient. The A-star cost function is f of n equals g of n plus h of n. The reason why the heuristic function is added is because this greatly optimizes computational performance in applications such as video games, as it ensures the search is directed toward the target rather than simply expanding outward in all directions. Now we can examine how this translates directly into in-game pathfinding. In the bottom left corner, we have a zombie NPC whose objective is to reach and attack the villager located in the top right corner. The zombie's AI sees everything within a 1-block radius as shown here. Within Minecraft, the game environment is essentially mapped as a grid graph, with the nodes being the corners of the blocks as shown in green. The algorithm then calculates the cost, which is g of n, to move to each adjacent node. As we know from the Pythagorean theorem, a diagonal movement, which is the hypotenuse, is generally cheaper than moving the two sides separately. This is why the NPC pathfinding in Minecraft usually favors diagonal movements. Now let's observe this algorithm in action. As I enable the zombie's movement, it is clear that its AI successfully follows the predicted shortest path to the villager. Now what happens if an obstacle is introduced within the direct path of the zombie to the villager? The underlying principle remains. The algorithm must find the overall cheapest weighted path to the objective. As you can see, once the zombie's AI detects that the current path is now blocked, meaning that the cost to proceed through that path is effectively infinite, it must re-evaluate. Due to the influence of the h of n heuristic function, it quickly identifies the next cheapest non-obstructed path segment that leads toward the final node. Now let's watch in-game as the algorithm recalculates the path and the zombie continues its objective to attack the villager.